Let us see the fiber optic communications. We know fiber optic communications have large applications in our day-to-day life also, especially in the field of communication of signals. Communication of signals using the optical waveguides forms the basis of fiber optic communication. So it is a method of transmitting information from one place to another place by sending pulses of light. So we will make the information in the form of, we will encode the information in pulses of light through an optical fiber. And this optical fiber will carry the information, that is the transmitting information from one place to another place. So information carrying capacity of a cable depends on the bandwidth. More the bandwidth, more will be the capacity of the cable to transmit the signal. So this is a block diagram of a fiber optic communications. So you have an information source. So maybe it's say anything, any source which generates a signal. For example, let's say a sound system which is producing the sound audio output. Then this must be converted into an electrical signal. For that we can use a transducer. So transducer is an equipment which converts the information in the form of electrical signal. So this electrical signal will be converted in the form of a laser light or an LED light that will be done with the help of an optical source. And thus the output of optical source will be a light. So this light will be allowed to pass through some channel. Channel means in optical fiber communication, you can use optical fiber as the channel. Then at the end, you can have a detector. This detector will convert this optical signal back into electrical signal. Generally, that is optical detector is generally an avalanche photodiode. Photodiode will be a kind of a detector. So this detector will be given to the receiver, and the receiver will give the output at the electrical receiver will convert it into the signal at the output, and in the destination you will get the signal. So, transducer converts the information from source to signal, then laser or optical source electrical signal to optical signal, and optical channel is the optical fiber, and optical detector converts, this is not signal, optical detector converts the optical signal into electrical signal. Now let us understand the physics of this propagation of light in an optical fiber. Before that, we should have an idea about optical fiber. Optical fiber is nothing but a very transparent conduit, as a thin, which is very narrow, very small size of the order of micrometer. It is having a, that means it is of the order of a human hair. Size is almost, diameter is almost equal to human hair, diameter of human hair. It is made up of a glass or a clear plastic, and it is designed to guide the light waves along the path. The basic principle of operation is physics is a principle of total internal reflection. So when light enters one end of the fiber, it undergoes total internal reflection from the side walls and travel down the length of the fiber along zigzag path. So the innermost layer is called the core. This is core, and above this innermost layer, concentrically, it is covered with a cladding. So always the core will have a refractive index N1, and it will be always higher than the refractive index of cladding N2, because for that, then only total internal reflection happens. The entire thing will be surrounded by another jacket or a buffer, which is made up of more layers of plastic provided for the protector. So let us consider a light which is enters into this optical fiber, which is incidenting on at the core cladding surface. So this is a core with a refractive index N1, and this is cladding N2. Core has some more refractive index, which is denser medium. So then only total internal reflection happens. So this is the axis of the optical fiber. This is let it be allowed to incident on this fiber at an angle alpha theta A, and the theta C, and this is theta C is the critical angle at which this total internal reflection occurs, and this angle. This angle means this is the angle subtended by this ray at this phase, at this core cladding interface. That is theta c. So that is phi c, and the ray which is incident at the angle theta c will be grease grease this core cladding interface like this. Then we know by Snell's law we can write the Snell's law. If I apply Snell's law at the core cladding surface, so this is a core and this is a cladding. Then then sine theta sine phi c by sine 90, right? So this is the angle of incidence. So this is the normal. So this phi c is the angle of incidence, and this is reflected like this, right? So with respect to normal, it is making angle 90 degree. So angle of incidence at this interface is phi c, and the angle of refraction is 90 degree, right? The ray is going like this, right? This is going like this. It is just grazing the interface. So sine n2 by sine n1 is equal sine theta c by sine I by sine r is equal to n2 by n1. That is our Snell's law. So sine phi c by sine 90 is equal to n2 by n1. That is sine phi c is equal to n2 by n1 because sine 90 is 1. So I can write the critical angle phi c is equal to sine inverse n2 by n1, and the angle subtended by the critical ray with the axis of the fiber is called critical propagation angle. So actual critical propagation angle is this theta c. So theta c is nothing but 90 minus phi c, right? So phi c is equal to 90 minus theta c, right? Phi c is equal to 90 minus theta c. So sine phi c is equal to sine inverse of sine, right? That means you will get sine phi c is equal to sine 90 minus theta c. That is cos theta c. So from that I can write the cos theta c is equal to n2 by n1, or theta c is equal to cos inverse n2 by n1. This angle is called the critical propagation angle. So theta c is called the critical propagation angle. Now this in terms of this critical propagation angle, I can find out, or simply critical angle, I can find out how much rays can be absorbed at this core cladding interface. So for that we are considering again a strip index optical fiber. Let N2 be the refractive index of the cladding, and N1 is the refractive index of the core. So N1 is greater than N2, and let the theta c be the angle of critical angle, and theta I is the angle of incidence, and phi is the angle of incidence at this point. Let the light enters into the fiber at an angle theta I. It refracts at an angle theta r, and strikes at the core cladding interface at an angle phi. So if phi is greater than theta c, right? That is critical angle. So if phi is greater than this phi c, then only total internal reflection occurs. Then we can apply the Snell's law as sine theta I by sine theta r at this phase, angle of incidence, angle of refraction. So sine theta I by sine theta r is equal to n1 by n0. Let n0 is the refractive index of the air, right? Refractive index of the medium from which light is entering into the fiber. So here I am applying at this interface, I am applying Snell's law. Then I will get sine theta I by sine theta r is equal to n1 by n0. So if theta I is increased beyond a limit, phi will drop below a critical value of phi c, and ray will escape from the fiber, right? So the largest value of theta I can occurs when phi is equal to phi c, and this value of theta is called acceptance angle. So from this triangle, that is triangle PQR, I can write sine theta r is equal to sine 90 minus y, that is cos y, right? So from the previous equation, I can write sine theta is equal to, so in this previous equation, sine theta I by sine theta r is equal to n1 by n0. Here sine r is equal to cos phi, right? So sine theta I by cos phi is equal to n1 by n0, right? So when phi is equal to phi c, that is theta is equal to theta I maximum, then that theta is called the theta A, that is the acceptance angle. That is the angle at which we can get to maximum, in that maximum light is getting into the fiber. So sine theta is equal to n1 by n0 into cos phi c. So again, applying Snell's law to core cladding interface, I can write sine phi c by sine 90 is equal to, in the similar way we applied in the previous slide, sine phi c by sine 90 is equal to n2 by n1, because this is again 90. So I can write sine phi c is equal to n2 by n1, or cos phi c is equal to root of 1 minus sine square phi c is equal to root of 1 minus n2 by n1 the whole square is equal to root of n1 square minus n2 square by n1, right? Now substituting in the previous equation, that is this equation, I will get sine theta is equal to n1 by n0 into root of n1 square minus n2 square by n1, or root of n1 square minus n2 square by n0, or theta A is equal to sine inverse root of n1 square minus n2 square by n0. So if the light is launched from air, then we can write n0 is equal to 1. Then the acceptance angle theta A becomes theta is equal to sine inverse root of n1 square minus n2 square. So the acceptance angle is defined as the maximum angle that a light ray can have, so that light, the entire light is properly propagated down the fiber. So if we incident the light with an angle greater than this acceptance angle, then corresponding energy will be lost. That means this angle, there is an extreme limit for this angle, up to which only you can get the information completely at the other end. So if that if you incident the light with an angle greater than this theta, that is the acceptance angle, then your energy will be completely lost. That means it will not go through the this fiber, and it will not undergo the total internal reflection. So corresponding energy will be lost. So in three-dimensional, light rays contained within the cone having a full angle of 2 theta are accepted and transmitted along the fiber. This is we have if you take the two dimension, this is not a angle. This is just, you will become like a conical shape like this, right? So instead of this theta, you have to consider this 2 theta, because it is, we are considering 3 dimension. So then 2 theta will become the acceptance cone. So in this, we have find the sine theta is equal to root of n1 minus n2 square. Sorry, theta is equal to sine inverse root of n1 square minus n2 square, right? In the previous slide, we have seen that theta is equal to sine inverse root of n1 square minus n2 square. The sign of this acceptance angle is called the numerical aperture. That is an important quantity in the fiber optics. So sine of theta is equal to root of n1 square minus n2 square. So this can be n1 square minus n2 square can be written as n1 plus n2 into n1 minus n2, or n1 plus n2 by 2 into n1 minus n2 by n1 into n1, just rearranging. So n1 plus n2 by 2 can be approximately written as n1. And if we define n1 minus n2 by n1 as a fraction refractive index, fractional refractive index changes delta, then this Na, numerical aperture, can be written as root of n1 into delta into 2n1, that is n1 into root of 2 delta. And this is an important equation which can be used to solve many of the problems. So if you know the refractive index n1 of the core, and delta is nothing but the relative refractive index changes, that is fractional refractive index changes, that is n1 minus n2 by n1, then we can find out the numerical aperture. So physically, it means the capacity of the fiber to gather the light. So the more numerical aperture you have, the more capacity the optical fiber has to gather the light. So its value depends only on the refractive index of the core and the cladding. It ranges from 0.13 to 0.5. So this now let us discuss the mode of propagation and the normalized frequency. These are the two terms which are associated with the fiber optic communication. Mode means number of possible paths of the light in an optical fiber. So number of modes in a fiber depends that a fiber can support depends on the ratio of diameter of the fiber, means diameter of the core and the wavelength. So diameter to wavelength ratio if you take, that will define the number of modes that a fiber can support. So normalized frequency or a V number, which is a relation connecting fiber size, refractive index, and wavelength, it is given as V is equal to root of 2 pi by A, 2 pi A by lambda into root of N1 square minus N2 square. Or it can be also written as 2 pi A by lambda into N1 into root of 2 delta. Delta we defined in the previous slide. V number determines the number of modes that can be propagated through a fiber. So V number represents number of modes that can be propagated in a fiber. That is the normalized frequency. Mode of propagation means number of possible paths of the light in the optical fiber. Now, these optical fibers are broadly classified into two: single mode fiber, SMF, and multi-mode fiber. Single mode fiber means the light mode is one, that is, light travels along only one path. If light travels along multiple paths, then it is called a multi-mode fiber. So core diameter will be very small in the case of single mode. It is 4 micrometer only. It is large comparatively. It is 100 micrometer almost in the case of multi-mode fibers. Except in V number is less than 2.403 in the case of single mode fibers. It is V square by 4 in the case of V square by 2 in the case of multi-mode fiber. Because this number of modes will be given by V square by 2 or V square by 4 in the case of multi-mode fiber. V square by 4 means if it is a graded index fiber. If it is a step index fiber, V square by 2. I will define this step index and graded index in the next slide. And acceptance angle, numerical aperture, relative index change, that is delta, all are small in the case of small single mode fiber, but it is large in the case of multi-mode fiber. Usually it is a step index type. Here it is generally it is graded index type. Step index means N1 of the refractive index of the core is uniform throughout. If refractive index of the core is made to vary gradually, then it is called a graded index fiber. So in the case of graded index fiber, refractive index of the core is made to vary gradually. That we will see in the next coming slide also. So these are the differences between step index and graded index fiber. In the case of step index, refractive index of the core is uniform throughout. It does not and undergoes an abrupt change in the core cladding boundary. But here it is made to vary gradually such that maximum at the center of the core. Diameter is 50 to 200 micrometer in the case of step index. If it is multi-mode, if it is single mode, it is 10 micrometer. If here it is 50 micrometer in the case of multi-mode. It is generally multi-mode only. The path of light propagation is zigzag here in the step index, but it is almost helical in the case of graded index. And attenuation is more in the case of multi-mode step index fiber, but in single mode it is less. Here attenuation in the graded index, it is attenuation is less. In step index, what happens is when the light is traveling, there will be some difference in the reflected angles. Then these so high angle rays arrive later than low angle rays, which will cause the dispersion resulting in distorted output. But in the case of graded index, light rays travel at different velocity in different paths because of the variation in the refractive index. At the outer edge, it travels faster, and nearer at the center, it is as compared with the rays at the center, outer edge travels faster. But almost all rays will be exit at the same time due to the helical path. Therefore, dispersion is negligible, so attenuation is also small in the case of graded index fiber. So this figure indicates this is a single mode step index fiber. So this is a core. Core has a uniform refractive index, constant refractive index. Then it's abruptly changing at these interfaces, right? So at N2 is less than N1. So this is in the case of single mode step index. Multi-mode step index means that it has different paths, right? Number of modes are high. But then also at the core, you have a constant refractive index. At the core cladding interface, your refractive index is abruptly changed. But in the case of graded, multi-mode graded index fiber, your refractive index is gradually changing by like this. It is maximum here, and it is decreasing like this and decreasing like this, right? So that is called a multi-mode graded induction fiber. So optical fibers have a very large application. They are used in medical field like light gates, as I mentioned, for mainly for imaging tools and also as a laser for surgeries. They are used in defense and government purposes like used as hydrophones for seismic waves and sonar. Sonar means this is a basically navigation equipment using the sound, and also as wiring in aircraft, submarines, and other vehicles. Also for field networking, it is used for data storage, data transmission, telecommunication. It is used, networking. It is used to connect the users and services using variety of network. Basically, data cable using data cable and industrial and commercial purposes it is used and also broadcast and cable TV etc. There also these optical fiber communications can be widely used.